Imagine floating in the silence of space, absolute darkness, vast emptiness, the kind of quiet that makes your ears strain for any hint of sound. Then, without warning, it hits you. A burst of radio waves so powerful it pierces the cosmic stillness, a signal from the depths of the universe that vanishes as quickly as it appeared. No warning, no explanation, just a fleeting whisper from the void. This isn't science fiction. These are real, unexplained galactic signals, cosmic mysteries that have left astronomers scratching their heads for decades. What could possibly produce such brief, intense bursts of energy? Are they natural phenomena, colliding stars, dying black holes, or something even more exotic? Or could they be something else entirely, something beyond our current understanding? These signals don't just challenge what we know about the universe, they force us to question whether we're truly alone in it. And today, we're diving deep into 30 of the most baffling examples ever recorded, each one a puzzle waiting to be solved. From repeating signals that pulse like a heartbeat to one-off blasts that defy all explanation, these cosmic anomalies have sparked wild theories and heated debates. Some scientists believe they're the death cries of distant stars, while others wonder if we're catching glimpses of advanced alien technology. Whatever the truth may be, one thing's certain: the universe is sending us messages and we're only just beginning to decode them. So buckle up, we're about to journey into the great unknown, where every signal holds a story and every theory could rewrite the textbooks. The cosmos is speaking. Are you ready to listen? The WOW signal is the kind of mystery that keeps astronomers awake at night. A single burst of radio waves so strange, so perfectly timed, that it still haunts the scientific community nearly 50 years later. On a summer night in 1977, Ohio State University's Big Ear radio telescope picked up a signal so powerful that it overwhelmed the equipment. It lasted just 72 seconds, barely a blip in cosmic terms, but its intensity and frequency were unlike anything observed before or since. The astronomer who first spotted the data famously scrawled, "Wow," in red ink across the printout, giving the signal its iconic name. What made it so extraordinary? The signal blasted at precisely 1420 MHz, a frequency that's silent in nature. No known celestial object emits radio waves at that exact wavelength. Even stranger, it matched the expected profile of an artificial transmission, as if someone or something had deliberately aimed a beacon toward Earth. And then, just like that, it vanished. Despite decades of searching, the signal never repeated, leaving scientists with nothing but questions. The theories range from the plausible to the downright wild. Some argue it was a passing comet reflecting sunlight, though no known comet was in the right position at the time. Others suggest it could have been a rogue satellite or a military transmission, but declassified records show no matching operations. Then there's the tantalizing possibility that it was exactly what it appeared to be, an interstellar broadcast from an advanced civilization, a single, fleeting hello across the void. The WOW signal remains a cosmic enigma, a ghost in the radio static that refuses to be explained. Whether natural anomaly or deliberate message, it's a reminder of just how much we still don't understand about the universe, and how thrilling it is when the cosmos throws us a curveball. Decades after its discovery, the WOW signal continues to spark heated debates and fresh theories, proving some cosmic mysteries only grow more intriguing with time. One of the most talked about modern explanations came in 2016, when an astronomer proposed a bold new idea. What if the signal wasn't alien at all, but something much closer to home? The hypothesis centered on two comets, 266P Christensen and 335P Gibbs, which happened to be passing through the same patch of sky where the Big Ear telescope was pointed that fateful night in 1977. Comets are known to release hydrogen clouds as they approach the sun, And since the WOW signal was detected at a frequency associated with hydrogen, the connection seemed tantalizing. But the scientific community wasn't convinced. Critics quickly pointed out a glaring flaw: those comets weren't even known to exist in 1977. Their discovery decades later meant they couldn't have been factored into the original analysis, and follow-up calculations showed their positions didn't quite line up with the signal's precise origin point. Even more damning, no other comet has ever produced a radio burst remotely like the WOW signal, leaving the theory on shaky ground. The controversy highlights a deeper challenge in astronomy: how do we interpret a signal we can't replicate? Without a second detection, the WOW signal remains frozen in time, a single data point in a sea of noise. Some researchers argue we're wasting energy chasing ghosts, while others insist it's worth revisiting old mysteries with new technology. Recent efforts have used advanced radio telescopes to scan the same region with far greater sensitivity, hoping to catch even the faintest echo of that 72-second burst. So far, silence. Yet the debate has pushed scientists to refine how we search for extraterrestrial signals altogether. Projects like Breakthrough Listen now analyze millions of radio frequencies simultaneously, filtering out cosmic static and human interference with algorithms that would have been unimaginable in the 1970s. Maybe we'll never solve the WOW signal, or maybe, just maybe, the next big discovery is already hiding in the data, waiting for another astronomer to circle it in red and write, "WOW." All over again. While the WOW signal left us with just one tantalizing glimpse, some cosmic transmissions refuse to stay quiet. And nothing proves that better than FRB 121102, the fast radio burst that broke all the rules. Discovered in 2012 by the Arecibo Observatory in Puerto Rico, this wasn't just another random blip from the void. Unlike the one-off bursts astronomers had catalogued before, this one came back again and again, over 60 times since its discovery, actually, pulsing with eerie regularity from a tiny galaxy 3 billion light-years away. What makes 121102 so baffling isn't just its stubborn repetition, it's the way its bursts behave. Most fast radio bursts are chaotic, unpredictable, like cosmic lightning strikes. This one, it follows a rhythm. During active periods, it fires off multiple bursts in under an hour, then falls silent for weeks or months before starting the cycle all over again. Even stranger, the signals are polarized, twisted in a way that suggests they've traveled through an intensely magnetized environment, something far more extreme than the space between galaxies. Theories about its origin swing between the awe-inspiring and the almost unthinkable. Some point to magnetars super-dense, highly magnetized neutron stars spinning so fast their magnetic fields could snap like rubber bands, releasing bursts of energy. But even the most violent magnetar eruptions can't fully explain the repeating pattern or the sheer energy behind 121102's blasts. Others suggest collisions between neutron stars or black holes, though those events are usually one-time cataclysms, not recurring performances. Then there's the far-out hypothesis that makes astronomers both cringe and lean in. Could these be artificial? The idea isn't as wild as it sounds. The burst's precision and energy could, in theory, match what we'd expect from alien propulsion systems. Imagine a civilization using directed energy beams to push light sails across interstellar distances. Even the polarization fits. Passing through a powerful energy-generating structure could twist radio waves exactly as observed, of course. Scientists caution against jumping to extraterrestrial conclusions, but 121102's stubborn strangeness keeps the door cracked open. What we do know is that this little repeater has rewritten the rulebook on fast radio bursts. Before its discovery, the field was split between one-off events and repeaters, with no clear link between them. Now, astronomers wonder if all fast radio bursts might eventually repeat. We just haven't watched long enough to catch them. telescopes from China's FAST to the Deep Synoptic Array in California now train their dishes on 121102's home galaxy, hunting for clues in its every flicker. One thing's certain, whatever's sending these signals isn't playing by nature's usual rules. Whether it's a magnetar with a secret, a cosmic collision in slow motion, or something far beyond our current science, 121102 is proof that the universe still holds puzzles we've barely begun to piece together. And the most thrilling part, this cosmic Morse code hasn't finished its message yet. Pinpointing 121102's cosmic address wasn't just a triumph of astronomy, it was a revelation that reshaped how we think about these mysterious signals. For years, fast radio bursts were like hearing a phone ring in a dark room. You knew the sound came from somewhere, but the source remained invisible. Then, in 2017, a team using the Very Large Array in New Mexico did the impossible. They traced 121102's bursts back to a tiny, unassuming dwarf galaxy 3 billion light-years away. The discovery was like finally seeing the caller ID on that cosmic phone, and what it showed was astonishing. This wasn't some massive, star-packed galaxy where you'd expect violent cosmic events. It was a humble, faint smudge of a galaxy, barely 1% the mass of our Milky Way, with frenetic star formation happening at its core. That detail alone sent theorists scrambling. If something this small could produce such powerful, repeating bursts, maybe the universe was littered with hidden sources we'd overlooked. Even more intriguing. The bursts were coming from a region near the galaxy's center where extreme conditions, like a supermassive black hole or a nebula swirling with newborn stars, could be twisting space itself into a natural radio amplifier. But the implications stretch far beyond astrophysics. The fact that repeating bursts like 121102 exist at all suggests they're fundamentally different from one-off fast radio bursts, possibly born from entirely separate phenomena. Some scientists now think repeaters might be powered by younger, more energetic magnetars, their outbursts fueled by the chaos of a freshly formed neutron star. Others speculate these bursts could be signatures of cosmic cataclysms frozen in time. Imagine two neutron stars locked in a slow-motion death spiral, their collisions sending shockwaves through space at regular intervals. And then there's the elephant in the room. Could any of this hint at intelligence? The dwarf galaxy's small size actually makes the alien technology argument both harder and easier to swallow. Harder because a civilization capable of engineering such powerful signals would stand out starkly against the faint backdrop of their home galaxy. Easier because if advanced life did arise there, the galaxy's compact nature might mean resources are concentrated, allowing a society to harness energy on staggering scales. Of course, the scientific community urges caution. Extraordinary claims require extraordinary evidence, but 121102's persistence keeps the conversation alive. What's undeniable is how much this one small galaxy has taught us. Its existence proves repeating fast radio bursts aren't flukes but a distinct class of cosmic phenomena, each repetition offering new data to decode. Future telescopes like the Square Kilometre Array promise to pinpoint hundreds more sources, potentially revealing patterns we can't yet see. Until then, 121102 remains a beacon literally pulsing from the depths of space, challenging us to listen closer and wonder, in a universe full of noise, what else might be trying to get our attention? Amid the cosmic static of everyday space noise, one signal stands out not for its power or repetition, but for where it seemed to be coming from. SHB-02+14a, detected in 2003 by the SETI at Home project, wasn't just another blip on the radio telescope. This faint, drifting signal appeared to originate near the same patch of sky where astronomers had once theorized an alien megastructure might exist, a region around a star called Tabby's star, already infamous for its bizarre flickering. The coincidence was enough to make even seasoned scientists pause. What made SHB-02+14 so unusual? It pulsed at approximately 1420 MHz, the same frequency as the WOW signal, a band silent in nature but ideal for interstellar communication because hydrogen, the universe's most abundant element, absorbs and emits energy at that wavelength. But here's where the plot thickens. The signal wasn't constant, it drifted. Most natural cosmic radio sources maintain a steady frequency, but SHB 02 plus 14 shifted slightly over time, as if the source were accelerating exactly what you'd expect if it were transmitted from a planet orbiting a distant star. SETI researchers noted this peculiar drift matched the motion of an Earth-like world circling its sun at roughly the same distance we orbit ours. The implications were staggering. Could this be a beacon deliberately tuned to a frequency any technologically advanced civilization might recognize? Skeptics, of course, rushed to offer less thrilling explanations. The signal was achingly faint, barely distinguishable from background noise, raising the possibility of instrumental error or terrestrial interference, a passing satellite or even a microwave oven left running near the observatory. Others pointed out that the star system in question was over 1,000 light-years away, making any intentional transmission an unlikely scenario. Why would a civilization beam a signal across such vast distances without knowing who or what might be listening? Yet the mystery lingers because science thrives on anomalies. SHB 02 plus 14A's drifting frequency remains unexplained by known natural phenomena, and its location in a star system already under scrutiny for unusual behavior keeps it on the shortlist of potential technosignatures. Projects like Breakthrough Listen have since revisited the region with more sensitive equipment, hunting for a repeat performance that never came. The signal vanished as quietly as it appeared, leaving behind a tantalizing question. Was it a cosmic coincidence, a technological glitch, or the faintest whisper of a hello we weren't quite ready to answer? What makes SHB 02 plus 14 so compelling isn't just its unresolved origin. It's a testament to how far we've come in our search for cosmic company. Unlike the WOW signal detected by chance, this was found by thousands of home computers crunching data for SETI at home, proving that the hunt for extraterrestrial intelligence has evolved from solitary astronomers to a global effort. And while the signal itself may remain inconclusive, it's a reminder that the universe is vast enough to hold possibilities we haven't even dreamed of yet. The next strange signal could be waiting in the data right now, hiding in plain sight until someone somewhere dares to take a closer look. SHB 02 plus 14A's eerie silence after its initial detection leads us to one of astronomy's most unsettling questions. If the universe is teeming with potential signals, why does the cosmos feel so profoundly, unnervingly quiet? This paradox isn't just about one faint transmission, it's at the heart of the Fermi Paradox, the glaring contradiction between the high probability of alien civilizations and the complete lack of evidence for them. Statistically, with billions of potentially habitable planets in our galaxy alone, we should be drowning in cosmic hellos. Instead, we're left straining to hear whispers like SHB 02 plus 14A, fleeting and ambiguous. So where is everyone? One chilling possibility is the Great Filter, a theoretical barrier that prevents life from advancing to the point of interstellar communication. The filter could lie in our past, meaning the emergence of intelligent life is so astronomically rare that we might be among the first, or even the only, species to make it this far. Alternatively, it might wait ominously in our future, a catastrophic event or technological trap that inevitably wipes out civilizations before they can spread across the stars. Nuclear war, climate collapse, artificial intelligence gone rogue, these aren't just dystopian fantasies but potential filters silently culling the cosmic herd. SHB 02 plus 14A's ambiguity makes it a perfect microcosm of this dilemma. If it was a genuine signal, its abrupt disappearance could suggest a grim fate for its senders. Civilizations might bloom briefly, broadcasting their existence before hitting some insurmountable wall. Or perhaps they're out there but have moved beyond primitive radio waves, communicating in ways we can't yet perceive, using neutrino beams or quantum entanglement, technologies that render our current searches hopelessly outdated. There's another, less apocalyptic angle, the zoo hypothesis. Imagine advanced civilizations observing us like animals in a galactic nature preserve, deliberately avoiding contact to let humanity develop undisturbed. In this scenario, signals like SETI 02+14 could be accidental leaks, the cosmic equivalent of a caretaker forgetting to mute their microphone. It's a comforting thought, but one that raises unsettling questions about who gets to play zookeeper in this universe. The truth is, every unexplained signal forces us to confront how little we know. SETI 02+14 might be static, a fluke, or it could be a single breadcrumb on a trail leading to answers we're not ready to face. As we keep listening, the silence itself becomes a message. Whether it's a warning, a challenge, or simply the universe reminding us of our solitude, one thing's clear: the stars have a lot more to say. We just need to learn how to hear it. When astronomers picked up the strange signal from Proxima Centauri in 2020, the entire scientific community held its breath because this wasn't some distant, anonymous star. This was our backyard. Just 4.2 light-years away, the closest stellar neighbor to Earth had seemingly coughed up a radio transmission so peculiar, it checked nearly every box for an artificial origin. Dubbed BLC-1, the signal appeared during observations by the Breakthrough Listen project, a sweeping initiative to scan millions of stars for signs of intelligent life. What made this detection different? It wasn't just the source, it was the signal's bizarre behavior. BLC-1 blipped at 982 MHz, a frequency usually silent in nature, often reserved for human-made satellites and aircraft. Even more intriguing, the signal drifted slightly, matching what you'd expect if it came from a planet orbiting Proxima Centauri, a system we already knew hosted at least 2 rocky worlds, one of which sits in the habitable zone. For a moment, it felt like science fiction might become reality. Had we just intercepted a transmission from the next star over, but science thrives on skepticism. As researchers dug deeper, inconsistencies emerged. The signal never repeated despite exhaustive follow-up scans. Its frequency drift, while tantalizing, could also be explained by terrestrial interference, perhaps a passing satellite or even a malfunctioning device on Earth. Then came the clincher. Further analysis revealed BLC-1's properties didn't quite match what you'd expect from a true extraterrestrial beacon. Instead of a narrow, focused transmission, it was messy and broadband-like, more consistent with human-made radio noise refracting through the atmosphere. By 2021, the signal was downgraded from potential candidate to likely interference, a reminder of how fiendishly difficult it is to separate cosmic whispers from Earth's constant electronic chatter. Yet BLC-1's story isn't just about a false alarm. It's a masterclass in the challenges of hunting for extraterrestrial intelligence. Proxima Centauri's proximity makes it both a prime target and a minefield of complications. Our own satellites, cell phones, and even microwaves can bleed into telescope data, creating false positives that mimic alien signals. The very thing that made BLC-1 exciting, its closeness also made it vulnerable to contamination. But here's the twist. While BLC-1 may have been a bust, Proxima Centauri remains a compelling candidate for life. Its confirmed exoplanet, Proxima b, orbits in the Goldilocks zone where liquid water could exist. Some scientists speculate that if life does exist there, it might not use radio at all, opting for more advanced communication methods like lasers or quantum signals. Future missions, like the Breakthrough Starshot initiative to send tiny probes to the Alpha Centauri system, could one day settle the debate by getting up close. BLC-1's rise and fall teach us something crucial about the search for cosmic company. Extraordinary claims demand extraordinary proof. Every flicker of hope must survive an onslaught of scrutiny, and even the most tantalizing signals can crumble under the weight of investigation. But that's the beauty of science. It's not about the answers we want, but the truth we uncover. And sometimes the most profound discoveries aren't the signals themselves, but the lessons we learn in chasing them. The story of BLC-1 didn't end with its demotion to likely interference. In many ways, that's where its real value began. This near miss became a catalyst for change, forcing astronomers to confront a harsh truth. If we can't reliably distinguish between a cosmic hello and a glitch in our own technology, how will we ever recognize the real thing? The signal's rise and fall exposed gaps in our detection protocols, pushing scientists to refine their methods with a level of rigor that could reshape the future of SETI. One immediate change was the adoption of stricter verification steps. Before BLC-1, a signal that matched certain criteria like drifting frequency or appearing in a quiet radio band might have sparked premature excitement. Now, researchers automatically assume terrestrial interference first, requiring multiple independent telescopes to confirm any candidate before raising alarms. It's the scientific equivalent of measure twice, cut once, and it's already preventing wasted effort on false leads. But the deeper lesson lies in embracing false positives as part of the process. In a field where the stakes, both scientific and cultural, are so high, skepticism isn't just useful, it's survival. Every potential signal must survive a gauntlet of tests, from checking satellite orbits to eliminating atmospheric effects. Even then, some ambiguities remain. BLC-1's messy, broadband-like qualities initially fooled experts because space is full of phenomena we haven't fully catalogued yet. Lightning on Jupiter, auroras on distant exoplanets, even the magnetic fields of rogue planets, all can mimic artificial signals in unexpected ways. This isn't discouraging, it's liberating. Each false positive teaches us something new about the universe's complexity, sharpening our tools for the next hunt. Projects like Breakthrough Listen now deploy machine learning to sift through millions of signals in real time, flagging anomalies with unprecedented precision. These systems learn from past mistakes, including BLC-1's quirks, to filter out earthly noise more effectively. The irony, the very interference that muddies our data, also proves how rare clean signals are. If space were buzzing with alien broadcasts, we'd have unambiguous detections by now. The silence isn't empty, it's meaningful. It tells us that intelligent life, if it's out there, isn't carpet bombing the galaxy with radio waves. Finding it will require patience, precision, and a willingness to be wrong again and again. BLC-1 didn't just make us better listeners, it reminded us that discovery isn't about the answers we expect, but the questions we're brave enough to ask. Before fast radio bursts had a name or even a clear identity, there was the Lorimer burst, a single, blinding flash of radio waves that rewrote astronomy overnight. Back in 2007, West Virginia's Green Bank telescope was scanning the sky for pulsars when something extraordinary happened. Buried in the data was a burst unlike anything ever recorded. 5 milliseconds of pure cosmic energy, packing as much punch as the sun emits in a month. The signal, later named after astronomer Duncan Lorimer, who led its analysis, streaked across the universe from 3 billion light-years away, vanishing before anyone could even blink. At first, the discovery was met with outright skepticism. The burst's intensity defied explanation, and its one-off nature made it feel like a glitch, maybe a malfunctioning satellite or a blip from Earth's atmosphere. But when follow-up observations failed to find a culprit, scientists faced a chilling possibility. They'd stumbled onto an entirely new cosmic phenomenon. The Lorimer burst wasn't just strange, it was impossible by the standards of known astrophysics. No star, no quasar, no known celestial event could fling that much energy across the cosmos in such a fleeting instant. Theories erupted like fireworks. One leading idea pointed to neutron star mergers, cataclysmic collisions so violent they ripple spacetime itself. When two of these ultra-dense corpses spiral into each other, the resulting explosion could, in theory, eject a shockwave of radio energy. But there was a problem. Mergers are rare, and the Lorimer burst's energy dwarfed even those estimates. Others floated the idea of cosmic strings, hypothetical, space-time-defying filaments left over from the Big Bang. If these strings snapped or tangled, they might release bursts of energy on scales we can barely fathom. It's a thrilling idea, but with no direct evidence for cosmic strings' existence, the theory remains in the realm of elegant speculation. Then came the real twist. The Lorimer burst wasn't alone. As telescopes grew more sensitive, astronomers began spotting similar blasts, some repeating, some not, scattered across the sky like cosmic breadcrumbs. What once seemed like a freak event turned out to be the tip of an iceberg, a whole new class of celestial fireworks. Today, we know these as fast radio bursts, but their origins remain as mysterious as ever. The Lorimer burst didn't just give them a name. It forced us to confront how little we know about the universe's most violent, fleeting moments and the most thrilling part. Every new detection reminds us that some of the cosmos' loudest shouts are still waiting to be decoded. The Lorimer burst didn't just baffle scientists, it ignited a revolution. Before that 5-millisecond blip, no one imagined the universe could produce such fleeting, titanic flashes of radio energy. But once astronomers knew what to look for, the floodgates opened. Telescopes around the world began scanning the skies with renewed focus, armed with software designed to catch these split-second anomalies, and the cosmos did not disappoint. Within a decade, hundreds of fast radio bursts were catalogued, each one a miniature mystery echoing across billions of light-years. What started as a solitary oddity became one of astronomy's most vibrant frontiers, reshaping how we measure and understand the vast distances between galaxies. These bursts aren't just cosmic fireworks, they're tools. Because FRBs traverse such immense stretches of space, their signals carry fingerprints of the material they've passed through. When a burst's radio waves encounter electrons floating between galaxies, they slow slightly, with higher frequencies arriving before lower ones. This dispersion effect acts like a cosmic odometer, allowing scientists to calculate the burst's journey with stunning precision. The more spread out the frequencies, the more stuff the signal has punched through, giving us a way to map the universe's invisible scaffolding of sparse gas and dark matter. It's as if each FRB is a flare shot through a foggy night, revealing the shape and density of the unseen. Some of the most exciting applications come from localized bursts, ones we've traced back to specific galaxies. By comparing an FRB's dispersion with its known distance, astronomers can measure the density of intergalactic space along its path. These measurements are helping to solve a long-standing puzzle. Where is the universe's missing ordinary matter? Theories predict far more atomic material than we've observed, but FRBs suggest it's hiding in diffuse clouds between galaxies, too faint to see directly. Every new burst sharpens the picture, turning what was once invisible into a measurable part of our cosmic maps, and the potential doesn't stop there. Imagine a future where FRBs serve as universal mile markers, their precise timings acting like GPS signals for spacecraft navigating between stars. Or consider how their extreme brightness could let us probe the universe's earliest epochs, back when the first galaxies were birthing stars in the dark. Some researchers even speculate that repeating bursts with their enigmatic patterns might carry encoded information not from aliens, but from the violent physics of magnetars or neutron star quakes we've yet to comprehend. The Lorimer burst was more than a discovery, it was a key unlocking a hidden layer of the cosmos. What once seemed like random noise is now a symphony of data, each note carrying secrets about the universe's structure, history, and maybe even its future. And with every new burst detected, we're reminded, sometimes the most fleeting signals leave the deepest marks. Of all the cosmic anomalies ever observed, few have sparked as much wild speculation or rigorous scientific debate as KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, this unassuming flicker of light became an internet sensation in 2015 when astronomers uncovered its bizarre behavior. Unlike any star ever recorded, Tabby's star didn't just dim slightly at regular intervals as planets might cause. Instead, it plunged in brightness by up to 22% in erratic, dramatic dips, sometimes for days, sometimes for weeks, with no discernible pattern. The fluctuations were so extreme, so unnatural, that even the most conservative scientists had to entertain the unthinkable. Could this be evidence of alien engineering on a staggering scale? The most tantalizing theory came from astrophysicist Jason Wright, who suggested the star's light might be blocked by something far beyond natural, a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harness a star's energy. Picture millions of solar collectors orbiting like a vast, intricate hive, their movements blotting out light in unpredictable ways. It was a concept ripped straight from science fiction, yet for a brief, electrifying moment, the data seemed to leave the door cracked open. But the universe rarely serves up easy answers. As telescopes swiveled toward Tabby's star, alternative explanations emerged. Detailed spectral analysis revealed the dimming wasn't uniform across all wavelengths, a telltale sign of dust, not solid structures. Tiny particles, perhaps from cometary fragments or interstellar debris, could scatter certain colors of light while letting others pass, matching the observations. Even more convincing, subsequent studies caught the star brightening unexpectedly, something dust clouds do as they disperse and reform, but a rigid megastructure wouldn't. Yet the mystery endures because the dust itself is weird. Normal dust from a star's planetary system would be warmer, radiating detectable infrared light. Tabby's star's dust is oddly cold, suggesting it might come from somewhere else entirely, maybe a recent collision of moons or a wandering interstellar cloud caught in the star's gravity. Others propose the star itself is unstable, prone to violent outbursts that belch out vast plumes of obscuring material. What makes Tabby's star so compelling isn't just the lingering uncertainty. It's how this one anomaly forced us to confront the limits of our knowledge. Before its discovery, no one thought to look for alien megastructures in telescope data. Now, entire research initiatives scan for similar anomalies, blending rigorous astrophysics with open-minded curiosity. Whether the answer turns out to be dust, aliens, or something even stranger, Tabby's star taught us an invaluable lesson. Sometimes the most profound discoveries begin with a flicker of light that refuses to make sense. Tabby's star hasn't stopped surprising us. Years after its initial discovery, this cosmic oddity continues to defy expectations, serving up fresh mysteries with every new observation. In 2021, astronomers watched in disbelief as the star's luminosity plunged yet again. This time in a series of rapid, jagged dips that looked nothing like the smooth, predictable dimming caused by orbiting planets. One particularly dramatic event saw the star's light drop by nearly 10% in just days, a fluctuation so extreme it would require an object half the star's width passing in front of it. For context, even a Jupiter-sized planet would only block about 1% of the light. So what's really going on here? The data keeps pointing toward dust, but not the ordinary kind we're used to. Detailed spectral analysis from the Los Cumbres Observatory revealed something peculiar. The dimming affects blue light more than red, a classic fingerprint of fine, diffuse particles scattering shorter wavelengths. But here's the twist. This dust isn't evenly distributed in a neat disk. Instead, it's clumpy and erratic, like a swarm of debris caught in chaotic motion. Some researchers propose a shattered moon or a recent planetary collision, scattering fragments across wildly uneven orbits. Others wonder if the star is surrounded by vast, misshapen clouds of interstellar dust, snagged from deep space as it travels through the galaxy. Yet even these explanations strain against the data. Normal dust should heat up and glow in infrared, but Tabby's star shows none of the expected thermal signatures. That leaves scientists grappling with an unsettling possibility. We might be looking at a completely new kind of astrophysical phenomenon. One bold hypothesis suggests the dust could be ultra-porous, like cosmic smoke. Fluffy aggregates of particles with so much empty space between them that they block light without radiating much heat. If true, it would rewrite our understanding of how circumstellar material behaves. The most fascinating development, Tabby's star isn't just dimming, it's fading overall. Long-term observations show its baseline brightness has dropped by nearly 15% over the past century, a decline unmatched by any known star of its type. Some theorize this could be the aftermath of a cataclysmic event, like a planet being torn apart by gravitational forces, its remains still casting a shadow. Others point to internal stellar activity, with the star undergoing bizarre, slow-motion convulsions we've never witnessed before. While the alien megastructure theory has faded from mainstream discussion, Tabby's star remains a litmus test for how we approach cosmic anomalies. Every new observation forces us to question what we think we know, reminding us that the universe is far stranger than our textbooks suggest. And with next-generation telescopes like the James Webb Space Telescope now trained on this stellar enigma, we might finally be on the verge of answers, or better yet, even bigger questions. One thing's certain, this star refuses to be ignored. Whether it's teaching us about exotic dust, cosmic collisions, or something we haven't even imagined yet, Tabby's star continues to challenge the very definition of normal in the cosmos. And for astronomers, that's the most exciting kind of mystery there is. In the summer of 1967, a young radio astronomer named Jocelyn Bell Burnell was scanning the cosmos when she spotted something impossible. A pulse so precise, so unnervingly regular, it seemed to defy natural explanation. Every 1.337 seconds, like clockwork, a burst of radio waves would streak across her charts, arriving with metronomic consistency. The signal, dubbed LGM-1 for Little Green Men, sent shockwaves through the scientific community. Could this be the smoking gun proof that we weren't alone in the universe? The pulses were too perfect, too engineered feeling to dismiss. Some researchers even quietly drafted papers on how to announce first contact without triggering global panic. But the universe has a way of humbling even the brightest minds. Further observations revealed the truth. These weren't alien transmissions at all. The pulses came from a rapidly spinning neutron star, its intense magnetic field funneling radiation into beams that swept past Earth like a cosmic lighthouse. The discovery earned these objects a new name, Pulsars, and a Nobel Prize for Bell Burnell's supervisor. Yet the LGM incident left an indelible mark on astronomy, teaching a lesson that still echoes through SETI labs today. The line between natural wonder and extraterrestrial hello is thinner than we think. What makes this blunder so valuable is how it reshaped the search for intelligent life. Before pulsars, the idea of an artificial cosmic signal was pure speculation. Suddenly, scientists had a concrete example of how alien transmissions might appear and how easily they could be confused with natural phenomena. The experience forced SETI to develop rigorous verification protocols. Now, any candidate signal must pass multiple filters. Is it coming from a fixed point in deep space? Does its frequency drift in a way that suggests planetary motion? Most crucially, can it be repeated? These safeguards prevent another LGM moment while sharpening our ability to spot the real deal. The irony, pulsars ended up being nearly as fascinating as aliens. These ultra-dense stellar corpses, often no larger than a city yet heavier than the sun, push the laws of physics to their limits. Some, like the famous Black Widow pulsar, rip apart their companion stars with gravitational fury. Others, like millisecond pulsars, spin hundreds of times per second with atomic clock precision. They've become cosmic tools, helping us test Einstein's relativity and even navigate spacecraft. Yet the LGM story's true legacy isn't just about avoiding mistakes, it's about embracing the thrill of the unknown. That initial leap to aliens wasn't reckless, it was a testament to science's willingness to chase bold possibilities. Today, projects like Breakthrough analyze millions of radio signals daily, knowing most will be pulsars, satellites, or static. But buried in that noise could be another LGM, a signal so strange, so inexplicable, that for one electrifying moment we dare to wonder if we finally heard a voice across the dark. The universe is full of pulses. The trick is learning which ones are saying hello. Pulsars may have dashed early hopes of an alien radio broadcast, but their true nature turned out to be something even more extraordinary. Cosmic lighthouses, spinning with such mind-bending precision they've revolutionized our understanding of the universe. Picture a neutron star, the collapsed core of a massive star that exploded in a supernova, packed so densely that a teaspoon of its material would weigh 1 billion tons. Now imagine this stellar corpse rotating hundreds of times per second, its intense magnetic field accelerating particles to near light speed, firing beams of radiation from its poles like a celestial strobe light. That's a pulsar, a natural particle accelerator and timekeeper rolled into one. What makes these objects so invaluable to science isn't just their raw power, but their predictability. The Crab pulsar, for example, flashes 30 times a second with a regularity that rivals atomic clocks. Its rhythm so unwavering that astronomers once used it to calibrate timekeeping standards on Earth. Others, like millisecond pulsars, spin even faster, their stability so precise that deviations as tiny as 1/1,000,000th of a second can signal the passage of gravitational waves warping spacetime around them. It's this reliability that's turned pulsars into interstellar laboratories, letting us test Einstein's theory of relativity with unmatched accuracy. When two pulsars orbit each other, as in the famous Hulse-Taylor binary system, their decaying orbits reveal energy lost to gravitational waves exactly as predicted, confirming a cornerstone of modern physics. But pulsars aren't just cosmic clocks, they're also tracers for the galaxy's hidden anatomy. As their beams travel through interstellar space, they interact with electrons and magnetic fields, subtly altering the signal in ways that let astronomers map the Milky Way's invisible structure. Some even serve as probes for dark matter, with anomalies in their timing hinting at unseen mass warping their paths. And in the future, networks of pulsars could act as a galactic GPS, guiding spacecraft with beams instead of satellites, a navigational system literally written in the stars. The irony is delicious. What we once mistook for alien engineering turned out to be something just as transformative. Pulsars didn't just teach us about the deaths of stars, they handed us tools to explore the fabric of reality itself. From testing gravity's limits to uncovering the universe's missing matter, these spinning relics are proof that sometimes nature's accidents are far more valuable than the discoveries we set out to make. And somewhere out there, another misunderstood signal might be waiting not as a false alarm, but as the next key to unlocking the cosmos. Just when astronomers thought they'd identified every possible source of radio interference, the universe, or rather Earth, had one more trick up its sleeve. Meet perytons, bizarre radio signals that mimic fast radio bursts almost perfectly, complete with the same sweeping frequency patterns that make cosmic signals so distinctive. First detected at Australia's Parkes Observatory in 1998, these phantom bursts had scientists scratching their heads for over a decade. Like fast radio bursts, they arrived suddenly, blipped across a wide range of frequencies, then vanished without a trace. But unlike their cosmic counterparts, perytons had one glaring anomaly: they only appeared during business hours. The breakthrough came in 2015 when researchers at Parkes noticed something peculiar. Whenever a peryton appeared on their instruments, someone in the observatory kitchen had just opened a microwave door mid-cycle. It turned out these alien signals were being produced by ordinary microwave ovens specifically. The split-second burst of radiation emitted when someone impatiently yanked the door before the timer finished. The sweeping frequency pattern that was caused by the microwave's magnetron powering down unevenly as the door interrupted its operation. Even more absurd, the signals only reached the telescope because they bounced off the observatory's metal walls and into the detector. This revelation wasn't just humorous, it was a wake-up call for radio astronomy. Perytons demonstrated how easily human-made interference could masquerade as cosmic phenomena, especially when that interference came from unexpected sources. Microwave ovens had been ubiquitous for decades, yet no one considered them a potential contaminant until the evidence became impossible to ignore. The incident forced observatories worldwide to implement stricter protocols, from banning microwaves near telescopes to developing advanced algorithms that can distinguish between terrestrial and extraterrestrial signals in real time. But the peryton saga also holds a deeper lesson about scientific progress. These false alarms weren't failures, they were necessary stepping stones. Each time researchers ruled out another source of interference, they refined their understanding of what a genuine cosmic signal should look like. Today, that hard-won knowledge helps astronomers sift through thousands of candidate signals daily, separating the celestial wheat from the earthly chaff with unprecedented precision. The next time you heat up leftovers, remember, your microwave isn't just reheating food, it's part of a cautionary tale about how easily the mundane can imitate the miraculous. And for astronomers listening to the cosmos, that's a lesson as valuable as any discovery. The hunt for extraterrestrial signals is as much about understanding ourselves as it is about scanning the stars. For every genuine cosmic whisper picked up by our telescopes, there are countless false alarms, blips and bleeps from satellites, cell towers, and even kitchen appliances that mimic the very signals we're desperate to find. This isn't just background noise, it's a deafening tidal wave of human-generated interference, turning the search for alien civilizations into a high-stakes game of cosmic signal versus earthly static. Take the case of the Russian radio telescope Ratan 600, which in 2019 detected a strong, narrowband signal from the direction of the star HD 164595. The excitement was short-lived. Within days, researchers traced the transmission to a passing Russian military satellite, its emissions accidentally mimicking the profile of an artificial interstellar beacon. These kinds of mix-ups aren't rare, they're the norm. Our planet is a cacophony of radio chatter, from GPS satellites to Wi-Fi networks, each one capable of masquerading as something extraordinary. Even natural phenomena like lightning or meteor trails can produce bursts of radio waves that fool automated detection systems. To combat this, SETI researchers have developed layers of defense against human-made noise. The first line, location. Radio telescopes like the Allen Telescope Array in California are deliberately nestled in remote valleys, shielded by mountains that block terrestrial interference. Then there's the tech itself. Modern algorithms compare potential signals against databases of known satellites and aircraft, flagging matches in real time. Some systems even use multiple telescopes thousands of miles apart. If a signal appears in one dish but not the others, it's likely local interference. But the most fascinating safeguard might be how SETI handles ambiguity. When Breakthrough Listen detects a promising candidate, it's subjected to the wow signal test. Could this be natural, human, or something truly unexplainable? The bar is intentionally high. A signal must lack all hallmarks of terrestrial origin. No frequency drift from satellite motion, no telltale sidebands from earthly transmitters. Even then, confirmation requires independent verification from separate observatories. It's a process designed to weed out hope from hype, ensuring that if we ever do announce contact, there's no room for doubt. Yet this vigilance comes at a cost. In filtering out so much noise, could we also be filtering out genuine signals? Some astronomers worry our assumptions about alien communication might be too narrow. What if extraterrestrial transmissions don't resemble our clean, narrowband radio beacons but something messier, something we're programmed to dismiss as interference? The irony is profound. The very tools we've built to find others might be the ones blinding us to their presence. The lesson here isn't just about technology. It's about humility. Every false alarm, every microwave oven mistaken for a cosmic hello, reminds us that the universe doesn't care about our expectations. The search for extraterrestrial intelligence is as much about untangling the noise of our own civilization as it is about listening to the stars. And perhaps that's the greatest challenge of all, not just to hear, but to truly understand what we're hearing. In 2016, the quiet star HD 164595 suddenly became the center of astronomical attention, not for anything it did, but for what seemed to be coming from it. A Russian radio telescope near Zelenchekskaya picked up a strange, powerful signal blasting from the direction of this sun-like star, located 94 light-years away in the constellation Hercules. The signal lasted just a few seconds, but its intensity and frequency profile sent shockwaves through the SETI community. Unlike the usual cosmic static, this transmission was narrowband, concentrated around 11 GHz, a range often associated with human-made satellites. But if it wasn't from Earth, the implications were staggering. What made this signal so tantalizing was its source. HD 164595 isn't just any star, it's a near twin of our Sun, slightly older and dimmer, but with the same metallicity and spectral type. More intriguingly, astronomers already knew it hosted at least one Neptune-sized planet. The possibility that a second, undiscovered world might orbit in the habitable zone, combined with the detection of a signal that matched no known natural phenomenon, sent imaginations into overdrive. For a brief moment, it felt like history might be repeating itself, evoking the same thrill and uncertainty as the WOW signal nearly 40 years earlier. But the excitement was short-lived. Within days, the signal's most likely culprit emerged, a Russian military satellite passing through the telescope's field of view. The timing matched, and the frequency profile aligned perfectly with known terrestrial transmissions. Even the signal's strength made sense. What seemed like an impossibly powerful broadcast from deep space was in reality a relatively faint emission magnified by the satellite's proximity. By the time astronomers finished their analysis, the consensus was clear. This wasn't a cosmic hello. It was just another case of human noise polluting the cosmic airwaves. Yet the episode sparked a fierce debate that had nothing to do with aliens. When news of the signal leaked to the media before peer review, headlines worldwide blared claims of a potential extraterrestrial detection, only to walk them back days later. The fallout exposed a rift in the scientific community. Should unverified signals ever be made public? Proponents of transparency argue that the public has a right to know about potential discoveries, especially when taxpayer-funded equipment is involved. They point out that crowdsourcing analysis, leveraging the collective brainpower of amateur astronomers and independent researchers, can accelerate the verification process. After all, the original detection of pulsars came from unexpected scrutiny of anomalous data. But critics counter that premature announcements risk eroding public trust in science. Every false alarm fuels skepticism, making it harder to convince the world when a genuine detection finally occurs. The HD 164595 incident also highlighted a growing practical challenge. Our skies are becoming noisier. With thousands of satellites now cluttering low Earth orbit, and tens of thousands more planned, the risk of interference grows exponentially. future telescopes may need to contend with constellations like SpaceX's Starlink, which already leave bright streaks across optical observations. Radio astronomy faces an even starker threat as satellite transmissions drown out the faint whispers of the cosmos. Some observatories are fighting back with advanced filters and AI-driven algorithms to scrub interference from their data, but it's an arms race with no clear end in sight. What's remarkable about this signal isn't what it was, but what it represents: a cautionary tale for the modern age of astronomy. As our technology advances, so too does our ability to confuse ourselves. The universe is vast enough to hold endless mysteries without us inventing new ones, and perhaps that's the real lesson of HD 164595. Before we can hear the cosmos, we first need to learn how to listen. The HD 164595 incident wasn't just a lesson in signal analysis. It was a masterclass in how quickly scientific curiosity can spiral into a media circus. Within hours of the detection leaking online, headlines blared breathless claims like "Have we found aliens?" and "Russian telescope picks up possible extraterrestrial signal." Never mind that the observation hadn't been peer-reviewed or that the researchers themselves urged caution. The story took on a life of its own, fueled by our collective fascination with the idea of cosmic neighbors. This frenzy highlights a dangerous disconnect between how science operates and how the public consumes it. Authentic scientific discovery is slow, methodical, and rooted in skepticism. Every claim must survive brutal scrutiny before earning acceptance. But media ecosystems thrive on immediacy, boiling complex research into clickable soundbites that prioritize excitement over accuracy. The result: a cycle where unverified signals get amplified into breaking news, only to be quietly debunked days later when deeper analysis reveals mundane explanations. The damage isn't just to reputations, it's to public trust. Every overhyped maybe that fizzles into a "never mind" makes it harder for the next legitimate discovery to be taken seriously. Yet the blame doesn't rest solely with journalists. Scientists and institutions sometimes play into the hype, whether by leaking premature findings or couching uncertainty in language that sounds more definitive than it is. The SETI community walks a particularly tightrope. On one hand, they rely on public interest to secure funding and telescope time. On the other, they risk crying wolf if they trumpet every unexplained blip as a potential breakthrough. The HD 164595 signal could have been a teaching moment, a chance to showcase the rigorous verification process that separates wishful thinking from verified discovery. Instead, it became another case study in how not to handle ambiguity. There's a better way forward. Imagine if every preliminary detection came with built-in context, clear disclaimers about the likelihood of terrestrial interference, reminders that extraordinary claims require extraordinary evidence, and transparent timelines for follow-up observations. Projects like Breakthrough Listen now adopt this approach, pairing press releases with detailed technical appendices that let enthusiasts dig into the data themselves. It's a small step toward bridging the gap between scientific nuance and public understanding. The stakes are higher than they seem. If humanity ever does detect a genuine extraterrestrial signal, the world's reaction will depend on how well we've prepared the public for the possibility. Will it be met with thoughtful discussion or knee-jerk sensationalism? The answer hinges on rebuilding trust, one cautious headline, one responsibly communicated finding at a time. Because the universe isn't just sending us signals, it's testing whether we're mature enough to interpret them. Most cosmic mysteries hide in stillness, flickering stars, vanishing signals, silent voids. But what happens when the universe itself seems to be moving in ways that defy everything we know? Enter the dark flow, an anomaly so unsettling it challenges our understanding of reality itself. While not a signal in the traditional sense, This phenomenon has astronomers questioning whether entire galaxy clusters might be caught in a cosmic current, one that could hint at forces beyond our visible universe. The story begins with the cosmic microwave background, the afterglow of the Big Bang that permeates all of space. In 2008, a team analyzing data from NASA's Wilkinson microwave anisotropy probe noticed something bizarre. Hundreds of galaxy clusters, each containing thousands of galaxies, were drifting in the same direction at nearly 2 million miles per hour, as if pulled by some invisible hand. This wasn't random motion, it was a coordinated flow, like leaves caught in a river we can't see. The researchers called it dark flow, and its implications were staggering. At first, skepticism ran high. Could this be a measurement error or an artifact of incomplete data? After all, the cosmic microwave background is notoriously difficult to interpret, with tiny fluctuations holding clues to the universe's structure. But follow-up studies using the Planck satellite and X-ray observatories only deepened the mystery. The flow persisted, stretching over billions of light years and involving thousands of clusters. Whatever was causing it had to be unimaginably massive, far beyond the gravitational pull of any known supercluster or dark matter concentration. This is where theories get wild. One leading idea suggests the dark flow might be evidence of something outside our universe, a neighboring cosmos exerting gravitational influence through the fabric of spacetime itself. Picture two soap bubbles floating close together. Even if they never touch, the gravity from one could tug on the other. If true, this would be our first glimpse of a multiverse, a concept straight out of theoretical physics that suddenly seemed testable. Other explanations stay within our universe but push the limits of known physics. Some propose vast, undiscovered structures made of exotic matter, cosmic filaments or domain walls acting like invisible magnets on a galactic scale. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, might be unevenly distributed, creating currents in the cosmic sea. Yet dark flow remains controversial. Critics argue that peculiar velocities, the natural motion of galaxies, could add up to mimic a coordinated flow. Others point to subtle biases in how we measure galaxy cluster movements. The debate highlights a fundamental challenge in cosmology. When you're studying the universe as a whole, there's no outside reference point to confirm what's moving and what's standing still. What makes dark flow so compelling isn't just the science, it's the philosophical weight behind it. If confirmed, this could be evidence that our universe isn't the only one, that we're part of something vastly larger and stranger than we ever imagined. Or it could reveal gaps in our understanding of gravity, dark matter, or the very nature of spacetime. Either way, the anomaly reminds us that the cosmos still holds surprises on the grandest scales, and that some currents might be flowing where we least expect them. The dark flow doesn't just challenge our understanding of the universe, it threatens to rewrite the entire cosmic rulebook. If galaxy clusters are truly caught in this inexplicable current, it raises a staggering possibility. Our universe might not be alone. Some cosmologists argue the flow could be the first tangible evidence of something beyond our cosmic horizon, a neighboring universe exerting gravitational influence on our own. It's a theory ripped straight from the edges of theoretical physics, where the idea of a multiverse has long been debated but never proven. Imagine standing on the shore of an ocean, feeling the tug of a hidden tide, except this tide isn't made of water, but of entire galaxies being pulled towards something we can't see, can't measure, and can barely comprehend. What makes this multiverse hypothesis so tantalizing is how it fits with existing theories. Inflationary cosmology, which describes the rapid expansion of the early universe, suggests that our cosmos might be one of countless bubble universes floating in a vast, higher dimensional space. Each bubble could have its own laws of physics, its own dimensions, even its own versions of time. Most of these universes would be forever out of reach, separated by impassable voids. But if two bubbles formed close enough, their gravitational fields might subtly interact, creating a cosmic tug of war that manifests as the dark flow. It's a fringe idea, but one that suddenly seems less like science fiction when faced with the sheer scale of this anomaly. Yet the multiverse isn't the only explanation on the table. Another camp argues the dark flow could be evidence of structures so vast, they redefine what we thought possible within our own universe. Picture a cosmic web stretching billions of light years, woven from dark matter and galaxies, with density variations so extreme they create gravitational currents capable of moving entire clusters. Some models even suggest these structures could be remnants of the universe's birth, primordial wrinkles in space-time left over from the Big Bang, invisible to our telescopes but detectable through their gravitational fingerprints. Of course, skeptics aren't convinced. They point to the limitations of our measurements, how small biases in data or incomplete maps of galaxy motions could create the illusion of a flow where none exists. Others suggest the phenomenon might be a quirk of relativity, a trick of perspective where our local motion makes distant clusters appear to move in unison. The debate is a microcosm of modern cosmology's biggest challenge, distinguishing between genuine anomalies and the limits of our tools. But whether the dark flow is real or not, its very existence as a controversy reveals how much we still don't know about the universe's architecture. The most profound implication isn't about parallel universes or hidden structures, it's about humility. For centuries, we've assumed the cosmos operates by rules we can uncover, that every mystery has an answer within our framework of physics. The dark flow, if confirmed, would be a stark reminder that the universe might not care about our frameworks. It could be hinting at forces beyond our current theories, dimensions beyond our perception, or even neighbors beyond our cosmic horizon. And that's the real thrill of the hunt, not just solving puzzles, but discovering that the puzzle itself might be far bigger than we ever imagined. Tabby's star may have stolen headlines with its bizarre flickering, but there's another layer to this cosmic enigma, one that crackles with radio static rather than dimming starlight. In 2017, the Green Bank Telescope in West Virginia turned its massive dish toward this stellar oddity, hoping to catch whispers of radio waves that might explain its erratic behavior. What it found was just as perplexing as the star's optical antics: sporadic bursts of radio emission, flaring up unpredictably before fading back into silence. These weren't the steady hum of natural astrophysical processes. They were sharp, transient pulses, the kind that set SETI researchers' pulses racing. Could this be the missing piece, evidence that Tabby's star's strangeness wasn't just about dust or debris, but something far more intentional? The signals themselves were tantalizingly ambiguous. Unlike the smooth radio glow of a typical star, these bursts were clustered in time, arriving in short, intense windows rather than a continuous stream. Their frequencies were also peculiarly narrow, focused around specific wavelengths instead of smeared across the spectrum as natural emissions tend to be. To some astronomers, that specificity raised eyebrows. Narrowband signals are a hallmark of engineered communications, whether human-made satellites or, hypothetically, alien beacons. Even more intriguing, the burst seemed loosely correlated with the star's optical dimming episodes, as if whatever was blocking the light might also be generating these radio whispers. But before diving headfirst into the extraterrestrial hypothesis, scientists had to wrestle with more mundane explanations. One leading theory proposed that the radio burst stemmed from heightened stellar activity, perhaps monstrous solar flares erupting from Tabby's star, orders of magnitude more powerful than anything our sun produces. These flares could accelerate charged particles, generating radio waves as they spiraled through the star's magnetic field. The timing with optical dimming might then be coincidental or linked to the same underlying turbulence. Supporters of this idea pointed to similar, if less extreme, radio bursts from young, magnetically hyperactive stars. Then came the plot twist. Further observations revealed a puzzling inconsistency. the radio signals didn't always align with optical dimming and sometimes appeared when the star's light remained steady. This decoupling muddied the waters, suggesting that if the radio bursts and light dips were connected, their relationship wasn't straightforward. Some researchers floated the idea of a swarm of exocomets' icy bodies vaporizing as they plunged toward the star, releasing both dust to dim the light and ionized gas that could generate radio noise. Others speculated about interactions between the star's magnetic field and a hypothetical planet with a magnetosphere far stronger than Earth's, creating sporadic radio auroras visible across interstellar distances. Of course, the elephant in the room remained the possibility of artificial origins. The notion of a Dyson swarm, a vast array of energy-collecting megastructures, gained fresh traction with the radio detections. If an advanced civilization were building such constructs, they might rely on powerful wireless energy transfer between components, inadvertently leaking radio signals as a byproduct. The irregular timing could reflect construction phases or shifting energy demands, while the narrowband pulses might trace back to focused transmission beams. Even skeptics admitted the scenario wasn't impossible, just extraordinarily unlikely without more concrete evidence. What makes Tabby's star's radio signals so compelling isn't just their mystery, but what they represent in the broader search for cosmic company. They're a reminder that anomalies often come in pairs or trios, or more layering confusion atop curiosity. The star's optical dimming forced us to reconsider how planetary systems form and evolve. Its radio bursts challenge our assumptions about how stars and potential technologies might announce their presence. And while the most thrilling explanations linger on the fringe, they push us to refine our tools, sharpen our questions, and stay open to the universe's capacity to surprise. For now, Tabby's star keeps its secrets. Future telescopes, like the Square Kilometre Array, may finally unravel whether these radio whispers are stellar tantrums, celestial coincidences, or something far more extraordinary. Until then, they stand as cosmic breadcrumbs, inviting us to keep looking, keep questioning, and stay humble in the face of the unknown. After all, the universe rarely serves its mysteries one at a time. The key to unraveling cosmic oddities like Tabby's star might not lie in bigger telescopes, but in ones that never blink. Enter the Vera Rubin Observatory, a revolutionary facility perched high in Chile's Atacama Desert, poised to conduct the most ambitious stellar census ever attempted. When its 8.4-meter mirror opens its eye to the sky in 2025, it won't just observe the cosmos, it'll watch it, night after night, capturing time-lapse movies of the southern sky with a camera the size of a small car. This relentless gaze could finally crack cases like Tabby's star by doing something no previous telescope could, providing uninterrupted surveillance of millions of stars simultaneously, turning fleeting anomalies into solvable puzzles. What sets the Rubin Observatory apart isn't raw power, but endurance. Traditional telescopes might glimpse a star like Tabby's dimming once or twice a year if they're lucky. Rubin's 10-year legacy survey of space and time will monitor each patch of sky roughly 1,000 times, building ultra-high-resolution light curves for billions of objects. Imagine having security camera footage instead of scattered snapshots. Suddenly, erratic dimming events become trackable patterns. Is Tabby's star's behavior random, or does it follow hidden cycles? Are its light dips preceded by subtle changes in brightness? Rubin's avalanche of data could spot correlations invisible to sporadic observations. The observatory's secret weapon is synoptic capability, the ability to survey vast swaths of sky repeatedly with surgical precision. While most large telescopes focus on tiny cosmic targets like cosmic scalpels, Rubin operates as a wide-angle floodlight, scanning the entire southern sky every few nights. This approach transforms anomaly hunting from a needle in a haystack struggle into a systematic investigation. Stars exhibiting even the faintest flickers will trigger automated alerts, flagging them for deeper study. And Tabby's star isn't alone. Rubin could discover thousands of similar oddballs, revealing whether it's a cosmic fluke or part of a broader stellar phenomenon we've barely begun to notice. But Rubin's potential goes beyond spotting weirdness. It could decode it. By cross-referencing light curves with spectra from other telescopes, astronomers might distinguish between competing explanations for erratic dimming. Dust clouds, for instance, scatter blue light more than red, while solid objects block all wavelengths equally. If Rubin catches a dip, follow-up observations could immediately determine whether the culprit is likely comet fragments, planetary debris, or something entirely novel. The observatory's real-time data pipeline means the astronomy community can react to surprises within hours, not years. The implications ripple outward. If Rubin detects coordinated dimming across multiple stars, perhaps clustered in specific regions of space, it could hint at interstellar objects or even technosignatures passing through our galactic neighborhood. Conversely, if Tabby-like stars prove extremely rare, it might suggest their behavior stems from freak events like recent planetary collisions, making them brief cosmic fireworks rather than long-term mysteries. Rubin's true legacy might be normalizing the abnormal. By exposing how often stars misbehave when we actually watch them closely, it could rewrite textbooks on stellar evolution. Maybe flickering like Tabby's star isn't strange at all. Maybe we've just been missing the bigger picture. In a universe where most revelations come from unexpected outliers, having an unblinking eye on the sky ensures we won't just find answers. We'll learn which questions we should have been asking all along. Gliese 581G wasn't just another exoplanet, it was a battleground. Nestled 20 light-years away in the constellation Libra, this rocky world sparked a firestorm when astronomers first claimed to have detected faint, repeating radio signals from its direction in 2010. The excitement wasn't just about the signals, it was the planet itself. Orbiting within the habitable zone of its red dwarf star, Gliese 581G seemed tailor-made for life, with conditions that might allow liquid water to pool on its surface. For a brief, electric moment, the world wondered, had we found not just a potentially habitable planet, but one that might be trying to talk to us? The signals in question were achingly subtle narrowband pulses at around 1420 MHz, the same frequency as the WOW signal and ASTROPHYSICS 02+14a. Detected by the Arecibo Observatory, they appeared to repeat in a way that didn't match any known natural astrophysical process. But almost immediately, skepticism took hold. The planet's very existence was disputed. Some teams couldn't replicate its detection in follow-up observations, arguing the data might be statistical noise misinterpreted as a world. Without consensus on whether Gliese 581G was even real, the signals it allegedly emitted became mired in controversy. Here's where the story twists. The signals weren't the work of aliens or even of the planet itself. Further analysis revealed they were likely terrestrial interference, possibly from satellites or ground-based equipment. But the real lesson of Gliese 581G isn't about false alarms. It's about the razor's edge astronomers walk when hunting for faint whispers in a universe drowning in noise. Detecting a signal from a specific exoplanet requires near-impossible precision. Even if Gliese 581G exists, its star's activity, red dwarfs are notorious for violent flares, could easily drown out any artificial transmission. Add Earth's own radio pollution and the challenge becomes Herculean. Yet the debate reshaped how we approach the search for extraterrestrial intelligence. Gliese 581G forced scientists to confront the limits of their methods. If we couldn't agree on whether a planet 20 light-years away existed, how could we trust claims about signals from its surface? The controversy spurred new protocols, like requiring multiple telescopes to independently verify detections before announcing potential discoveries. It also highlighted the need to study host stars' behavior exhaustively, since stellar activity can mimic or mask artificial signals. What lingers, though, is the tantalizing possibility Gliese 581G represents. Even if those initial signals were noise, the hunt for transmissions from habitable exoplanets isn't over. Future telescopes, like the Square Kilometre Array, will scan stars like Gliese 581 with unprecedented sensitivity, filtering out interference with AI-driven precision. And while we may never know if that particular world harbors life, its legacy is clear. It taught us to listen more carefully, question more deeply, and remember that the universe's quietest signals are often the hardest and most rewarding to hear. Gliese 581G's greatest mystery isn't whether it sent signals, it's whether the planet even exists at all. This cosmic tug of war between discovery and doubt exposes the brutal challenges of hunting for habitable worlds, especially when they orbit temperamental red dwarf stars. The initial excitement in 2010 was understandable. Here was a rocky planet, possibly just 30% more massive than Earth, nestled perfectly in its star's Goldilocks zone where liquid water could flow. But that's where the simplicity ended. Almost immediately, other research teams failed to replicate the detection, arguing the planet's gravitational pull on its star, the method used to find it, was actually just noise in the data, stellar activity masquerading as a world. Red dwarfs like Gliese 581 are notoriously rowdy parents. These small, cool stars frequently erupt with violent flares that can strip atmospheres from orbiting planets while creating radio interference that mimics artificial signals. Even if the planet does exist, its chaotic stellar environment makes it a nightmare to study. Unlike quieter sun-like stars, where subtle planetary influences are easier to spot, red dwarfs drown out delicate measurements with magnetic tantrums. This noise isn't just an observational hurdle, it's a cosmic curtain that might be hiding countless habitable worlds we simply can't see yet. The controversy cuts deeper than one disputed planet. Gliese 581G became a case study in how wishful thinking can shape science. When researchers reanalyzed the data years later with more advanced techniques, some concluded the original team had essentially overfit their models, subconsciously tweaking parameters until they found what they hoped to see. It's a cautionary tale for the exoplanet age, where the line between statistical noise and new worlds grows thinner with every discovery. Yet the drama also revealed something revolutionary about how we define habitability. Even if Gliese 581G is real, its close orbit to a flare-prone star means it's likely tidally locked, with one side permanently scorched and the other frozen. Early assumptions that such worlds couldn't host life are now being challenged by models showing how atmospheric currents might redistribute heat. Suddenly, the habitable zone isn't a neat band but a spectrum of possibilities, where survival depends as much on a planet's resilience as its location. What began as a debate over radio signals became a masterclass in cosmic humility. The universe doesn't care about our tidy definitions or detection limits. For every promising world we find, there may be a dozen Gliese 581G's ghosts in the data that force us to question not just what we see, but how we see it. As telescopes grow more powerful, they won't just reveal new planets. They'll expose how much we still have to learn about the very meaning of habitable. Space isn't supposed to make noise, at least, not the kind you can hear. The vacuum between stars should be utterly silent, sound waves having no medium to travel through. Yet satellites orbiting Earth keep picking up something strange. Eerie, low-frequency booms and rumbles that seem to roll through the cosmos like distant thunder. Scientists call them space quakes, and they're among the most unsettling acoustic anomalies ever recorded. These aren't sound waves in the traditional sense, but vibrations in Earth's magnetic field, converted into audible frequencies. And what they reveal about our planet's invisible shield is as fascinating as it is terrifying. One of the most dramatic examples occurred in 2014, when NASA Van Allen probes detected a massive pressure wave pulsing through the magnetosphere, the protective magnetic bubble surrounding Earth. The event lasted just minutes, but its intensity was staggering. Imagine a seismic wave, but instead of moving through rock, it rippled through lines of magnetic force at over 100,000 miles per hour. When translated into audio, the result sounded like a deep, resonant boom followed by eerie whistling, as if someone had struck a cosmic gong. The source: a sudden gust of solar wind, the stream of charged particles constantly flowing from the sun, had slammed into our magnetosphere hard enough to make it ring like a bell. But not all space booms have such clear origins. Some appear seemingly at random with no correlating solar activity. In 2017, the European Space Agency's cluster mission recorded a series of unexplained percussive perturbations near Earth's magnetic tail, the elongated region opposite the Sun, where the magnetosphere stretches like a windsock. These vibrations had a bizarre musical quality, oscillating between frequencies like a poorly tuned radio. Theorists scrambled for explanations, proposing everything from magnetic reconnection, events where tangled field lines snap and release energy, to interactions with mysterious plasma waves coursing through the solar system. Perhaps the strangest aspect of these cosmic soundtracks is how deliberate they sound. When NASA Themis satellites captured ultra-low frequency waves in the magnetosphere, the resulting audio files could easily pass for a sci-fi film score, pulsing rhythms, rising and falling tones, even what sounds like metallic pings. One particularly haunting recording, dubbed the chorus by researchers, consists of whistling waves that resemble distant birdsong, except these birds are electrons spiraling along magnetic field lines at nearly light speed. The implications stretch far beyond eerie audio clips. These vibrations act like diagnostics for Earth's magnetic health, revealing hidden fractures and pressure points in our planetary shield. Each boom or whistle maps interactions between solar wind and our magnetosphere, helping predict potential disruptions to satellites and power grids. Some researchers even speculate that advanced civilizations might use similar electromagnetic music to communicate across interstellar space, encoding messages in the very vibrations we're only beginning to understand. Yet for all we've learned, space remains a symphony of the unexplained. Every new satellite brings fresh mysteries, growls from Jupiter's magnetic field, clicks from Saturn's auroras, even a bizarre plasma roar detected by Voyager as it crossed the solar system's boundary. The cosmos might be silent to human ears, but its electromagnetic heartbeat tells a different story, one where invisible forces collide, resonate, and occasionally scream. And the most thrilling part, we're just starting to tune in. The idea that space is utterly silent is one of astronomy's most persistent myths. While it's true that sound waves can't travel through the vacuum, the cosmos is far from mute. It's just waiting for us to listen in the right way. By converting electromagnetic vibrations into audible frequencies, scientists have uncovered a hidden symphony of crackles, whistles, and booms echoing across the universe. These aren't sounds in the traditional sense, but something far stranger. Electromagnetic waves translated into something our ears can process, revealing a side of space we rarely get to experience. Take Jupiter, for example. When NASA Juno spacecraft dipped close to the gas giant, its instruments picked up something eerie, a chorus of screeches and pops caused by charged particles slamming into the planet's magnetic field. Scientists call these Jovian plasma waves, and when sped up to audible frequencies, they sound like a horror movie soundtrack. The most unsettling of these is the Jovian Dawn Chorus, a series of rising whistles that mimic birdsong, except these birds are electrons spiraling along magnetic field lines at nearly the speed of light. It's a reminder that even in the void, physics has a way of creating rhythms we instinctively recognize. Then there's the haunting melody of Saturn. The Cassini spacecraft, before its fiery plunge into the planet's atmosphere, recorded something known as Saturn's radio emissions. When translated into sound, these emissions resemble a slow, ghostly wind howling across an alien landscape. Researchers traced these vibrations back to the interaction between Saturn's magnetic field and the solar wind, a turbulent dance of energy that creates oscillations in the plasma surrounding the planet. The result is an almost musical resonance, one that shifts in pitch as solar activity ebbs and flows. But perhaps the most dramatic cosmic sounds come from black holes. In 2022, NASA Chandra X-ray Observatory took data from the Perseus galaxy cluster, home to a supermassive black hole, and sonified the pressure waves rippling through its surrounding gas. The original waves were far too low for human hearing, but when scaled up 57 octaves, they revealed a deep, pulsing hum like the world's largest bass note. This sound isn't just eerie, it's ancient. Those waves have been traveling through space for over 2 billion years, carrying with them the reverberations of one of the universe's most violent phenomena. Even Earth contributes to this cosmic orchestra. The Van Allen radiation belt's donut-shaped zones of charged particles trapped by our planet's magnetic field produce something called magnetospheric hiss. When played back, it sounds exactly like static from an old radio, except this static is the sound of particles scattering through the upper atmosphere. During geomagnetic storms, when solar wind buffets our magnetosphere, these hisses morph into sharp cracks and pops like distant fireworks. What makes these sounds so captivating isn't just their strangeness, it's what they teach us. Listening to space lets scientists diagnose magnetic fields, track solar storms, and even probe the density of interstellar plasma. The same way a doctor uses a stethoscope to hear a heartbeat, astronomers use these electromagnetic vibrations to monitor the health of stars, planets, and galaxies. And who knows, maybe one day we'll stumble upon a signal that doesn't just reflect natural chaos, but something far more deliberate. Until then, the universe's hidden soundtrack remains one of its most mesmerizing mysteries, proving that even in silence, space has a voice. For decades, conspiracy theories have swirled around a mysterious object dubbed the Black Knight satellite, allegedly an ancient alien spacecraft orbiting Earth for 12,000 years. Stories claim it's been transmitting signals since the dawn of human civilization, that NASA has covered up its existence, and that it even appears in medieval tapestries. The reality, this cosmic boogeyman is a patchwork of misidentified debris, Cold War secrecy, and outright fabrication, one of the internet's most persistent space myths. The myth's modern incarnation began in 1954 when newspapers reported that the U.S. Air Force had detected two mysterious satellites orbiting Earth, impossible at the time, since no country had yet launched one. The story was later retracted, but the seed was planted. Fast forward to 1961, when astronaut Gordon Cooper allegedly spotted a glowing green object during his Mercury mission. Conspiracy theorists latched onto this, claiming it was the Black Knight, though Cooper himself later clarified he'd seen nothing unusual. The final piece fell into place in 1998, when NASA STS-88 mission photographed a strange, angular object during construction of the International Space Station. Internet forums erupted, proof of the Black Knight at last, except it wasn't. The STS-88 image actually showed a thermal blanket lost during a spacewalk, its crumpled surface catching sunlight in ways that made it look eerily artificial. As for earlier sightings, they trace back to mundane explanations, misinterpreted radio echoes, discarded rocket parts, even a 1928 Norwegian experiment that bounced signals off the ionosphere, later misconstrued as alien transmissions. The supposed medieval tapestry connection, a creative misreading of a Bayeux tapestry panel showing a comet, not a satellite. The most fascinating twist isn't the myth's falsehood, but how it persists. The Black Knight thrives because it taps into our love of hidden histories and shadowy cover-ups. It's a modern legend stitched together from half-truths, its longevity proof that in the absence of clear answers, imagination rushes in. Perhaps the real mystery isn't about satellites at all, it's about why we're so eager to believe the cosmos is hiding secrets just out of reach. NASA could debunk this myth daily and it wouldn't matter. The black night endures because it's not really about space, it's about our longing for the universe to be stranger, grander, and more mysterious than it is. And in that sense, it's a legend that's always orbiting just beyond the reach of facts. The Black Knight legend isn't just a story, it's a mirror reflecting something fundamental about us. In a universe so vast and silent, the idea that we might not be alone is intoxicating. Myths like these persist because they fill a psychological void, offering narratives where cold, empty space suddenly feels inhabited, even watched over. Think about it, a 12,000-year-old satellite implies that someone out there noticed us long before we could notice them, that Earth mattered enough to monitor. That's a far more comforting thought than the alternative that we might truly be adrift in an indifferent cosmos. This longing for cosmic companionship isn't new. Ancient cultures projected gods and heroes onto the stars, turning constellations into mythic figures. Today, with the gods of Olympus long retired, we've replaced them with advanced aliens and derelict spacecraft. The Black Knight taps into the same archetype, the mysterious watcher, the hidden guardian. It's no coincidence that the myth gained traction during the Cold War, when humanity first reached into space but still viewed it as a battleground. A silent alien observer offered a narrative where we weren't just rival nations launching missiles, but a species worthy of extraterrestrial attention. The internet transformed these whispers into shouts, fragments of truth, a lost thermal blanket, a misheard radio transmission became pixels in a grand conspiracy mosaic. Online communities amplified the myth, not because they're gullible, but because they're hungry for wonder. In an age where satellites and space stations are routine, the idea that something unexplained might still orbit us is thrilling. It's the same impulse that fuels ghost stories around campfires, the hope that just beyond the edge of the known, something magical lingers. Science itself plays an unintentional role in keeping these myths alive. Every time astronomers discover a bizarre signal or an odd celestial object like Tabby's star or Oumuamua, the public imagination leaps to aliens. These aren't failures of science communication, they're proof of how deeply we crave mystery. The unknown is a blank canvas, and we'd rather paint it with extraterrestrial engineers than accept that some phenomena simply defy our current understanding. But there's a flip side to this desire. The same myths that inspire wonder can also distort real science. When every anomaly is framed as potential alien technology, it risks trivializing genuine discoveries. Imagine spending years studying a pulsar's radio signature, only to have your work overshadowed by viral claims of alien messages. The tension is real. How do we nurture curiosity without letting it override skepticism? Perhaps the answer lies in redirecting that hunger for the extraordinary. The universe doesn't need invented watchers to be awe-inspiring. Real phenomena colliding neutron stars, magnetic monsters like magnetars, even the delicate chemistry that might seed life on icy moons, are every bit as wondrous as any myth. The Black Knight will likely keep orbiting our collective imagination, but the true magic is realizing that the cosmos, even without ancient satellites, is stranger and more beautiful than any story we could invent. In the end, these myths are less about aliens and more about us, our fears, our hopes, our need to feel connected to something greater. They remind us that exploring space isn't just about mapping stars or decoding signals. It's about navigating the vast, uncharted territories of our own curiosity. And that journey, with all its detours into myth and mystery, is what makes the cosmos feel alive. Of all the cosmic visitors to our solar system, none have sparked as much debate or outright bewilderment as Oumuamua. When this interstellar interloper was first spotted in 2017, it defied every expectation. Unlike any known asteroid or comet, this reddish, cigar-shaped object tumbled through our neighborhood at blistering speeds, leaving astronomers scrambling to explain its impossible behavior. The most perplexing detail, its acceleration couldn't be accounted for by gravity alone. As Oumuamua hurtled away from the sun, something was giving it an extra push, and that's when the theories exploded from skeptical to sensational. At first, scientists assumed outgassing was the culprit, the same process that gives comets their glowing tails. As ices heat up and vaporize, the escaping gas acts like a natural thruster, subtly altering an object's trajectory. But Oumuamua showed no visible coma or tail, no telltale signs of volatile substances boiling off its surface. Alternative explanations poured in. Maybe it was made of molecular hydrogen ice, an exotic material that could sublimate invisibly in sunlight. Others suggested tidal forces might have stretched it into that peculiar elongated shape during a close encounter with some distant star, turning it into a cosmic slingshot projectile. Then came the hypothesis that made headlines worldwide. Harvard astronomer Avi Loeb proposed Oumuamua could be artificial, a light sail or derelict probe from an advanced civilization. The math was tantalizing. Its flattened shape and unexpected acceleration aligned eerily with how a thin, reflective sail might behave under solar radiation pressure. The idea wasn't entirely far-fetched. Humanity's own Starshot initiative plans to send wafer-thin probes to Alpha Centauri using similar technology. Could Oumuamua be someone else's Starshot drifting silently through the cosmos? But here's where Occam's razor slices through the speculation. The simplest explanation, that Oumuamua was a fragment of some unknown but natural process, still holds weight. Recent studies suggest it might have been a shard torn from a Pluto-like exoplanet, rich in nitrogen ice that vaporized undetectably. Others propose it was a cosmic dust bunny, a porous agglomeration of interstellar debris so light that solar photons could nudge it visibly. The truth is, we've only just begun cataloging objects from beyond our solar system. Oumuamua might seem bizarre simply because it's our first sample, not because it's truly anomalous. The real lesson of Oumuamua isn't about aliens or exotic ices, it's about humility. This tiny visitor exposed how little we know about the materials and processes shaping other star systems. Future telescopes like the Vera Rubin Observatory will likely spot dozens more interstellar nomads, building a census that puts Oumuamua into context. Until then, it remains a cosmic Rorschach test, a mirror reflecting our hopes, our biases, and our boundless curiosity about what else might be sailing silently through the dark. The mystery of Oumuamua might have only scratched the surface of what's drifting between the stars, and the next generation of telescopes is about to crack the cosmic vault wide open. Upcoming observatories like the Rubin Observatory's Legacy Survey of Space and Time, or LSST, are poised to revolutionize our hunt for interstellar visitors, scanning the skies with such relentless precision that objects like Oumuamua won't just be rare curiosities, they'll be catalogued by the dozens. Unlike traditional telescopes that focus on narrow patches of sky, LSST will photograph the entire southern hemisphere every few nights, creating a time-lapse map of the cosmos so detailed it could spot a refrigerator-sized object passing through our solar system. What makes this so groundbreaking isn't just the volume of discoveries, it's the quality. Oumuamua's fleeting visit left astronomers scrambling to gather data before it vanished into the void. But with LSST rapid-fire imaging, future interstellar objects won't slip away unnoticed. The telescope's hypersensitive camera could capture their rotations, surface compositions, and even potential outgassing in unprecedented detail. Imagine an object like Oumuamua, but with weeks or months of observations instead of days, enough data to distinguish whether its acceleration came from natural ices vaporizing or something more exotic, like light pressure pushing against a flat, reflective surface. The real game-changer, LSST's ability to detect patterns. If multiple interstellar visitors share Oumuamua's peculiar shape or acceleration, it might hint at a common origin, perhaps debris from colliding exoplanets or fragments ejected by dying stars. But if one stands out starkly, exhibiting traits that defy natural explanations, the implications could be staggering. Picture an object with a perfectly geometric silhouette, or one emitting narrowband radio pulses as it tumbles through space. LSST won't just find these objects, it'll give us the tools to interrogate them, and the hunt won't stop at LSST. The European Space Agency's Comet Interceptor mission, slated to launch in 2029, will loiter in space, waiting for a pristine interstellar object to cross its path. Once one's spotted, the spacecraft will rocket toward it, capturing close-up images and spectra that could reveal everything from its chemical makeup to potential surface markings. Combine that with the square-kilometer array's ability to scan these visitors for artificial radio emissions, and we're no longer passive observers, we're active investigators, armed with the tools to answer, once and for all, whether any of these wanderers carry signatures of intelligence. The most tantalizing prospect isn't just finding another Oumuamua, it's finding something stranger. An object moving at unnatural velocities, or one that changes trajectory without a clear natural cause, would force us to confront possibilities we've only dared to imagine. Projects like Breakthrough Watch are already designing protocols to scrutinize such anomalies, filtering out cosmic noise to focus on signals that truly defy explanation. We're standing on the brink of a new era where the line between natural and artificial becomes blurrier with every discovery. The universe has spent billions of years scattering its debris across the stars. Now, for the first time, we're building the tools to sift through that debris and perhaps, just perhaps, find a message in the chaos from the eerie precision of the wow. Signal to the head-scratching accelerations of Oumuamua, these 30 cosmic enigmas have one thing in common: they refuse to play by the rules. Each one, whether a repeating fast radio burst from a distant dwarf galaxy or the haunting whispers of Tabby's star, forces us to rewrite the textbooks. Some, like the dark flow, hint at forces beyond our universe, while others, like the Black Knight legend, remind us how easily the line between myth and mystery blurs in the vast unknown. Take 121102, the fast radio burst that pulses like a cosmic metronome. Is it a magnetar's death cry or something more? Then there's the unsettling silence around Gliese 581G, a planet that might not even exist yet sparked debates about interstellar broadcast. And who could forget the Lorimer burst, the 5-millisecond flash that launched an entire field of astronomy, proving the universe loves to catch us off guard. These aren't just puzzles, they're invitations to dig deeper, to question harder. Theories abound, from the plausible to the fantastical. Maybe some signals are alien megastructures or light sails drifting between stars. Perhaps others, like perytons, are cosmic pranks, microwave ovens masquerading as extraterrestrial hellos. But even the false alarms teach us something vital. The universe is louder, weirder, and more unpredictable than we ever imagined. Every unexplained blip pushes scientists to build better tools, dream bigger ideas, and stay humble in the face of the unknown. That's the real magic here. These mysteries aren't dead ends, they're launch pads. Each one chips away at our assumptions, proving how much we still have to learn. And with breakthroughs like the Vera Rubin Observatory coming online, the next decade promises even wilder discoveries. Imagine catching another Oumuamua early enough to chase it, or decoding a fast radio burst that finally spills its secrets. The cosmos isn't done talking. So stay curious, hit subscribe to join us as we track these unfolding sagas, because the next big reveal could drop any day. And drop your own favorite theory in the comments. Do you think Tabby's star is hiding alien tech or just a bizarre dust storm? Is the dark flow proof of parallel universes or a quirk in the data? The conversation is just as important as the science. After all, the universe doesn't give up its secrets easily, but when it does, you'll hear it here first. Until then, keep looking up. The next signal could be the one that changes everything.